So the first speaker is Alessandro Roggero from the University of Washington, and the topic is nuclear dynamics and current generation quantum devices. Go ahead, Alessandro.
Thank you, Martino. And also, I want to start by thanking all the organizers for the invitation to speak at this very, very interesting workshop. So in my presentation today, I want to share with you some of the experience me and my collaborator have been developing in the past year and a half or two, while trying to run quantum simulations of real-time dynamics of nuclear systems on current generation devices. And in particular, I want to try and emphasize the important role of the noise and the challenges that are present when you are trying to fight noise and decoherence in these near-term devices. So let me start with a couple of slides of introduction to the kind of physics we are trying to do. So in nuclear physics, we are interested in a variety of dynamical processes happening across a very wide range of energy scales, going from dynamics of quarks and gluons up in the GeV scale, down to collective motion of the form nuclei that are happening at like fraction of a keV energy scales. Okay. Now we know that all of this very rich phenomenology can in principle be derived directly from the fundamental theory of QCD, so directly by solving the QCD Lagrangian that I brought up here. This is in principle. Now in practice, however, solving directly the QCD Lagrangian might not be a good idea for low energies. And that's because at low energies, quarks and gluons cease to be the relevant degrees of freedom. And therefore, it's more efficient and controllable to instead use effective field theories that are working directly with the degrees of freedom that are relevant for a given energy scale. So in most of my talk, essentially in all of my talk, I will be mostly concerned about theories where the energy scales are like below the pion mass, so that the relevant degrees of freedom are point-like baryons. And we describe the dynamics of these baryons by using a non-relativistic Hamiltonian, where we have 2 and 3 body interactions. Okay. Now these Hamiltonians are derived and constrained by both experiments and results from QCD. Okay. Now the advantage of using effective theories is that solving for, say, the spectrum of this Hamiltonian is much easier than not solving for the QCD ground states. And since we are doing effective theories and we are exploiting separational scales, this theory also describes correctly the low energy physics at least. Okay, so it's a good idea to use effective field theories if you're interested in the low energy part. Now, despite being simpler than solving QCD, solving this problem is still extremely challenging. And that's because these interactions are very strong, and therefore the structure of the ground state or the low energy space, it's very non-perturbative. And it requires large computational resources. And that's why effectively solving this problem has kept busy computers since the 1960s, from the pioneering calculation of Kelos to nowadays, where entire computational facilities are used for nuclear physics calculations, like in this very nice work by Titus and collaborators, where they were computing properties of like systems with hundreds of nucleons. Okay. And this was being possible by both advances in algorithms and the availability of computers. Okay, so as I was saying, there has been a great advantage or a great advance in computing static properties of nuclei, even large ones. On the dynamical side, however, things are a bit more complicated. So just to give you an idea of dynamical observable that is very important for nuclear physics, let me tell you about the response functions. So you've seen already talked about response functions a couple of days ago from Alessandro and Krishnan. The idea here is that we are trying to describe an inclusive scattering process where we are sending some probe to scatter off a nuclear target. And we are only measuring the final state of the probe without looking at what happened to the target. Okay. Now, the cross-section for this process can be completely characterized by a response function, which you already seen in Alessandro's talk. And essentially, it's the probability of having transitions from the ground state of the target to any possible final state, with a constraint that energy has to be conserved in this process. Okay. This operator Ho here essentially just specifies what the vertex of interaction between the target and the probe. Okay. Now, as you see here, these quantity is very complicated to calculate from first principles, because we need to know the whole spectrum of the Hamiltonian, essentially. Okay, so this is extremely challenging in practice, and there are techniques that are essentially computing similar quantities, and these are of omega. And so, for instance, the Euclidean response by Alessandro the other day. So these techniques allow us to essentially compute these kind of properties in systems that are medium-ish size, so like oxygens or carbon-12, for instance. Okay, and these techniques are relatively reliable, especially for like response functions which are very smooth, like say quasi-elastic peaks. But however, it's difficult to extend this to like open shell nuclei, large open shell nuclei, or for instance, computing exclusive scattering cross sections. Okay, and that's one of the main motivations to try and go and look at a different computational framework to try and tackle these problems. So this leads me to introducing quantum computing and quantum simulations more in general. So the idea of quantum simulation essentially was born by two main ideas in the early 80s. The first one was from Paul Benioff, where he essentially realized that one can use quantum mechanical Hamiltonian to essentially represent a universal computational device. Okay, in the same way that that a classical Turing machine can be described by a classical system. Okay, a couple of years after, Feynman conjectured that it should be possible to use a controllable quantum system, like say a system with ions trapped in an external potential that you have control on their motion, to simulate the behavior of a different quantum system that has a commensurate number of degrees of freedom. So, for instance, again, we can think of like mapping the degrees of freedom of a nuclear collision into degrees of freedom of a trapped ion system, and try to simulate the real-time dynamics of the nuclear systems using the controllable one. Okay, so this is very powerful in principle, and especially if you can map easily these two problems into each other. Okay, now to give you more or less an idea of how these kind of algorithms work in general, and what is the idea behind the advantage of these techniques, let me try to describe what a quantum computer is and how to use it in a very simplified fashion. Okay, so for the time being, I'm going to consider a quantum computer as a quantum black box, where you essentially are only told that the black box contains n degrees of freedom, which in our case we're going to consider as two-level systems, two-level quantum systems or qubits. Okay, and then you have a sequence of buttons on the outside that you can use to manipulate the system. So you have a button that initializes the state of the system in some fiducial initial state, this row. You have buttons to perform projective measurements on the system. And then you have a sequence of buttons that are performing operations on the degrees of freedom you have in the box. Okay. Now, a very important result that came out in the mid-90s, it's the Solovay-Kitaev theorem, which essentially tells you that it's possible to build a universal quantum black box, where by universal, I mean a quantum black box that can simulate any other quantum black box with not that much overhead. So you can build a universal black box using only a finite number of buttons. Okay, so this is critical if we want to actually build a universal black box in a lab, right? Because we need to be able to just calibrate a finite number of operations. Okay, so this is a very, very important result. And another very important result that came out in the 90s that relates to these quantum simulations is the result by Lloyd, where Seth Lloyd at MIT essentially he showed that by using these quantum black boxes, it's possible to simulate efficiently the time evolution of a quantum system that is described by local Hamiltonian. Where by local, I mean geometrically local Hamiltonian. Okay, and the idea behind this strategy can be described very quickly. So the first thing is that you want to discretize your physical problem, and that's essentially similar to what you're doing also in a classical situation. And you want to discretize both states and operators acting on states. After you've done that, you can essentially map the physical states, the discretized physical states, to states of your degrees of freedom, of your black box. Okay, and a good way of like representing this is by drawing lines representing your qubits or degrees of freedom, and blocks that are connecting different lines that are representing buttons you push to connect them. Okay, so in practice, if you want to do time evolution, you need to build a time evolution button and press it to evolve the qubits. Okay, The main result that Lodge showed was that if the interaction is local, you can decompose this time evolution button into a sequence of local buttons, okay, that are only coupling neighboring qubits, okay? So now, at this point, the idea is that a quantum simulation will essentially correspond to prepare the initial state and then push the right button sequence. And at the end, you just measure it, okay? This is extremely powerful because the number of buttons you have to push is only polynomially increasing in a system size, while in a classical simulation, that would be exponential, okay? So these ideas have spurred a lot of interest in quantum computing, but together with other results. And now we have a number of computational devices that have been built and that are available for experimentalists, for physicists to use. And this is extremely exciting, and it started to allow people to start to implement these ideas and look, for instance, at real-time dynamics of complicated many-body systems. Okay. So what I want to tell you about here are the first calculations trying to do real-time dynamics of systems that are relevant for nuclear physics. Okay, and the first steps towards this direction were done more on the high energy physics side of this. So for instance, these calculations here were trying to do real-time dynamics of field theories, both abelian U1s and also in Natalie's paper, SU2, non-abelian theory, with relatively small size machines. Okay. At lower energy, so in this like effective field theory kind of framework, last year we worked on try to look at the real-time dynamics of a very, very simple triton model. You will see that triton is between quotes, and the reason is because the approximation is relatively strong in the sense that we are discretizing a whole triton wave function over just 16 states. Okay, these allow us to essentially map the whole problem into just 4 qubits, which is great. But the problem is it's a very crude approximation of the triton, right, I would say. So once you map essentially these, once you discretize this problem in 16 states and you map the 16 states into states of the qubits, you can start to press the buttons to do time evolution. Okay. So for instance, what we were trying to compute here, so what I'm showing you here, it's the expectation value as a function of time of a 3-body contact density. So this essentially, it's the probability of finding all 3 nucleons in the same spot in space. Okay, that's a quantity that doesn't commute with Hamiltonian, so it does have some non-trivial evolution. And the blue line here is what we expected to see in an ideal simulation with infinite statistics and no noise. Okay, we implemented the algorithm, and the results from the machine look like this. So what you see here is that more or less at the qualitative level, the black points kind of follow the blue line, apart especially from at the very beginning. Okay. Now the reason why there is such a discrepancy is because the model I told you about before, this quantum black box model, it's not very realistic, especially in the near term. And the reason is because this black box is not living in vacuum. This black box is coupled to the environment, and that leads to the coherence. But also this black box, the buttons you build on this black box, you can only calibrate them to some given precision, which means that as you keep pressing more and more and more buttons, errors are going to start to grow up. Okay, so it's very, very important if you want to get reliable results out of current generation devices, and most likely for the near term, to essentially try to open up this quantum black box, try to look at the physical elements that are inside of it, and try to understand the noise sources. Okay, once you have a reasonable good handle of the noise sources that are happening in your device, then you can perform some techniques called error mitigation. And essentially you can, by measuring additional properties apart from just these black points and combining them with the black points, you can do a post-processing step where you're trying to correct for errors happening in the device. And what you see here, these green points here are the result of doing this error mitigation. And it works reasonably well in most of the time window here, apart you see at the very beginning times. Okay, the reason is because this kind of error mitigation techniques are able to essentially mitigate very efficiently some kind of errors, while others are way more difficult to do. And we believe that the nature of these errors here cannot be captured by our strategy. Okay, but in general, these error mitigation techniques are very, very powerful. Okay, and they allow you to get reasonable results out of current the machines. Okay, now let me just give you some ideas on how these error mitigation strategies work, especially a very simple one. So the strategy I want to tell you about is called the zero noise extrapolation, which was proposed in these first two papers here and then extended a lot in this PRX a couple of years ago. And the idea is the following. So imagine that you want to compute some observable in your quantum system, and your observable will be, and you have some finite noise into it. And this epsilon parameter here essentially just is a proxy to the strength of this noise. Okay. So the idea is that if you have a small amount of noise in your machine, then you can think of expanding any observable you compute out of the machine in a Taylor expansion, essentially in the noise. Okay. Now, if that's a good model for the noise dependence on an observable, then and you can also evaluate this expectation value at different values of the noise level, then you can use this model to extrapolate to zero noise. For instance, imagine that you can compute the expectation value of 2 points in noise. Then you can use the 2 points and do a linear fit and extrapolate to zero with this expression here. Okay. So what I'm showing you here on the right, it's a very nice paper by Eugene Dumitrescu and many of the organizers of the workshop. What you see here, the bottom, the x-axis here, it's a proxy to the noise level. So as you go on the right, the noise increases. Okay. I won't go into the details on how they actually increase the noise, but if you're interested, we can discuss more later. What you see here is that the value of expectation values at different levels of noise follows a very, very simple linear curve. Okay, and what we're doing here, essentially, we're computing these 4 different points at different noise levels and extrapolated to zero noise. Okay, in this particular case, it was extremely successful because, as you see, the noise was so low that essentially already the second order contribution weren't really changing data very much. Okay, now in general, we can think of generalizing this idea, and instead of using just a polynomial expansion, which is likely going to be meaningful only for small noise levels, we can also do parameterizations for large noise levels. For instance, exponentials are very useful in that regime there. Okay, so in general, if we have any good reason for writing down a model for the noise dependence, we can use it to extrapolate to zero noise. Okay, and so this idea leads me to give you the first of the questions that the organizers asked me to ask you, and it's the following. So we saw already, like, for instance, in Vitek's talk on Monday, that Bayesian methods and machine learning methods can be very useful when you want to do extrapolations in regimes that are outside of the data that you have. Okay, so a question that I have for you, it's that so right now these extrapolation techniques are done essentially by choosing a model to start with, believe in the model, and going with it. In the calculations we are doing, we usually use a multitude of models and try to do inference afterwards to find the best model. Okay, but that's a little bit crude. It should be possible to use a more kosher, if you want, Bayesian approach to find good models or do model mixing to try and do this extrapolation in a more controllable way. Okay, and something interesting, after we have these models that essentially are learning the noise process, can we use them to learn something about the physical noise process that is happening in this device? And for instance, after we train these models to learn this noise process, can we use them to detect, for instance, an hardware fault? Okay, because the devices that are going to be available in the near term are going to be a little bit finicky, in the sense that every once in a while you're going to get the wrong results, and that's just because the noise has a potentially very strong time dependence. Okay, and you want to be able to spot those situations and flag them. Okay, and I think since using Bayesian methods to model the noise can help us essentially looking for outliers in the results. Okay, so this will be very, very important, I think. So I told you about like this calculation of real-time expectation values, right? But at the beginning, I was telling you about response functions, right? So the calculation I showed you for the Triton, it's not really, you cannot really use it to compute response functions. You need to do one step more. And that's what I want to tell you about in this slide here. So one of the things that you can compute relatively easily on a quantum computer are two-point functions. Okay, so that's expectation value of a correlator of two operators of two different value points in time. Okay, and the reason why this observable is interesting is because it is the Fourier transform of our response function. Okay, so in a quantum computer, Rolando, Somma, and collaborators in Los Alamos have shown a long time ago now that computing this quantity on a quantum computer is relatively simple and only requires one additional qubit apart from the qubits you need to represent the psi zero. Okay, so recently we've been doing exactly this problem. So we used again our 4-qubit model for the Triton, added an additional qubit to essentially perform this 2-point function calculation. And these are preliminary results we got out of one of the possible 2-point functions that we get out of here. Okay. The only thing I want to say about this plot here is that what you see here are the black points are the bare result of the QPU, like the black points before. And what you see is that they are already very, very close to the exact ones. Okay. You see that you don't have very large fluctuations like you had before. Okay. The reason here is because these machines, the machine where these calculations were run are more modern and they have lower noises. Okay, they're also smaller. So the machine we used here is actually a 5-qubit machine. And the second thing I want to point out here is that the error mitigation, also in this case here, works extremely well in the sense that virtually all the points are compatible with the exact result within the 2 sigma error band. Okay. So we have more results about this problem here, and we are writing the paper right now. So you can expect to see some more updates in the not too distant future. Okay, good. So I told you about all of these calculations done in the near term, right? But for instance, computing the response function of this 16 mode problem is not that difficult classically, right? So at what point are we doing something that it's very challenging classically, okay? And in the paper where we worked out this Triton model, we also looked at the requirements in terms of number of operations, number of qubits, that you need to perform a realistic simulation of a response function that is useful for nuclear physics, okay? And the results are a little bit scary in the sense that if you want to get a realistic response for a medium mass nucleus, and in our case, we consider argon 40, which is very relevant for neutrino experiments like DUNE, for instance, you need about 4,000 qubits. And you need to push gate buttons, these local gate buttons, about 10 to the 8 times. Okay, to put this one in perspective, you might have heard that quantum computers are able to break cryptography, and in particular, they are able to break the RSA cryptography. To break a 4,000 bit RSA key, you need about the same number of button presses. Okay, and we don't expect to be able to break RSA in the near term. Okay, so this essentially tells you that running these simulations, it's not going to happen in the next 5 years. Okay, so we need to find ways around this issue. Okay, another way of, so let me use this plot here that I adapted from Google AI to explain more or less what this means in practice. Okay, so the y-axis you have here, it's the error rate, it's the maximum error rate in the machine, which you can think of as being the inverse of the maximum number of gates you can perform. Okay, so if we really wanted to do this calculation, we will need 4,000 qubits, so we will be around here, but we will need a noise rate 10 to the minus 8, okay, which is not realistic to have. Okay, in practice, what you can do, you can trade noise for qubits, and if you have enough qubits, you can do error correction, and that's not an issue. Okay, now in practice, we are not going to have these error corrected quantum devices anytime soon. Okay. What is more likely is that we're going to have relatively large devices with a few hundred qubits and noise levels 10 to the minus 3-ish, okay? Which means that, oh yeah, by the way, right now we are essentially here. So we are getting to the point where we have systems that are, we cannot simulate exactly in a classical setting, okay? But they're not still big enough that we can do the algorithms we would like to do. Okay, so some of the other questions I want to ask you are so given the fact that in a few years we will be able to have, say, about 200 qubits and about 2,000 gates, what can we, or better, what should we do with a machine like that? Okay, we won't be able to compute the response function of argon. So what should we do with that? And the second part that I also want the second point I want to raise is that, so these devices here are always going to live at some finite noise level, okay? And when you're trying to solve a problem in presence of noise, complexities might change dramatically, okay? So something that I think is worth thinking about is to think about whether or not the problem we are trying to solve on a quantum device, it's still complicated when we introduce noise into the problem, okay? There are situations where if you introduce a small amount of noise, the quantum algorithm you're trying to do can be simulated very efficiently classically, okay? So it might be possible that we can devise classical methods that are getting to the solution of problems we care about, exploiting the fact that we can perturb the problem with noise, and then it becomes simpler, okay? So this is something that is relatively very important, because we need to figure out problems that are robust against noise, in the sense that we want problems that we want to run around here that even if we add noise, they're still difficult to solve classically, okay? It's not completely clear what the boundaries of these problems are, but it's very important, I think, to think about the issue, okay? Now, before finishing up in the last like 4 minutes or so, I want to give you a little bit more, some more data points, if you want, to discuss better like these points. So in most of my talk so far, I thought about this real-time dynamics and the fact that those algorithms, essentially what you want to do, you want to decompose the time evolution operator into a sequence of gates that you press, right? So there is another very important class of algorithms that are used to prepare initial states and to compute static properties, okay? So they usually go under the name of variational quantum eigensolver, okay? So the idea here is that it's a variational algorithm where you're trying to prepare a state as close as possible to the ground state, okay? And the way you do it, you essentially apply some parameterized unitary to some variational initial state, and you try to minimize the energy with respect to the parameters, okay? So this is very similar to like what Giuseppe was telling about a few days ago in the classical setting, okay? In our case, we want to do it with a quantum computer, where essentially the parameterization is a unitary, and computing this expectation value is done by performing projective measurements on a quantum device, okay? So the idea is that using this technique, we can at least find relatively good unitaries that are preparing states close to the ground state, right? So for our Triton model, we started to try and use such a framework to prepare the initial state. And that's what we found. So this plot is a little bit crowded, so let me guide you through it. And by the way, I want to thank Andy Lee from Fermilab for making this great plot. So what you see here, the blue points are the energy that we measure. So this expectation value is a function of P as a function of time, okay? So the bottom panel here, it's time in days, okay? And the purple lines here are the number of individual quantum circuits that we are running on the real device, and we are getting expectation values out, okay? So the idea that every time you run a quantum circuit, at least for these machines, you need to resubmit your job to a queue, okay? So the reason why this is very heterogeneous is because of that, okay? So you can think of like, you're doing an optimization where every time you want to do an update, you need to resubmit a new batch job, okay? And the big issue here is a problem of latency, in the sense that it takes time. Like in this case here, it took like a week, okay, to get down to a reasonable number of parameters, okay, that give you a reasonable energy, okay? And that's problematic. So one way of getting around the problem is to use like more compact trial states or better optimizers. So for instance, in this case here, we didn't really use gradient information, and that's maybe why it was taking so many evaluations, okay? Now, the second problem, even if you have a week to wait to get your parameters, the problem is that when you're doing this fit, you're essentially, the parameters will depend on the noise of the machine, which means that you have a finite amount of time to use those parameters, okay? So what we did here was, after we got the parameters, we kept track of the energy as a function of days. And what you see here is that after a week or so, the energies, our Triton became unbounded. And the reason is because the machine was recalibrated and the noise model in the machine changed, and we had to redo the whole thing again, okay? So the problem is persistence, in the sense that even if you have the week to wait to get your parameters, you have a finite number of days to rerun it. Okay, so the point I want to make in this part here is that we should be careful about try to optimize very large cost functions in quantum devices, especially because of these issues. Okay, so I'm getting very close to the end. So let me just flash the summary conclusions. So I briefly told you at the beginning that advances in computing are allowing us to compute static properties of medium mass nuclei relatively reliably right now. However, like computing dynamical properties is still very complicated. Okay, and we need new ideas. Quantum computing have the potential to bridge the gap and allowing us to explore this new physics. And right now we have the first quantum devices that are available that are allowing us to explore at least some of these ideas. And something that is going to be very important to make the best use of these devices is to devise error mitigation strategies that are able to reduce the impact of noise on these devices as much as possible. Okay, that will be critical in the near term. So let me just now thank my collaborators for the results I showed you here. And let's just flash the questions I had during the talk to you. Thanks very much for your attention.
Thanks so much, Alessandro. So we do questions in the same way as we had before. You can raise your hand. We also have questions in the chat here. There's one from Abdul Hamid. Is there a way to optimize the number of buttons?
Yes. So the idea, so usually what you do, you choose a library of buttons you like, okay? Because for instance, your device can implement them very nicely. And then much of the formal development in quantum algorithms is trying to find the combination of buttons that is the smallest possible, okay? So it's usually relatively easy to show results like the scaling of the number of buttons, like if it's polynomial, with what power, things like that are relatively easy. It's much more complicated to start and look at like what the prefactors of that are, because prefactors of those scalings depend on the actual device you have, the layout of the qubits, and how you actually do those things. Okay, so yes, you can optimize the number of buttons, and that's like one of the main goals of like algorithmic design. You want to really try to minimize the number of pushes you have, right? But that changes a lot depending on the library of buttons you have. Yeah.
Then there's one from Jane. How is the noise controlled practically?
How is the noise controlled practically? In what sense?
There's one in one of your early slides, actually.
Like something like this. Yeah, I'm not sure I understand the question.
Yeah, because it came in the chat roughly towards the middle of your talk. But okay. Yeah, here comes a more one. Yeah, is there some external parameters that controls for the noise?
Oh yeah, so ish, in a sense that you have external parameters you don't have control over. Like, well, some you do, like temperature, right? But other external parameters are, for instance, other qubits, in the sense that so all the results I'm showing you here are obtained on superconducting devices, where you have a two-dimensional array of qubits, okay? And a big part, especially of the errors that you have at the beginning, it's the fact that in these devices here, you have sort of mid-range interactions that are coupling all of your qubits together electromagnetically, which means that when you're trying to modify the state of one qubit here, you're also modifying the neighboring ones, okay? And that's one of the main sources of errors, especially at the very beginning, okay? So if you want, the parameter that you have is like which qubit you pick and how many neighbors that are doing something non-trivial you have. So you can more or less tune that one a little bit, but you don't really have that much control because those interactions are mid-range. So they're really coupling essentially everybody with everybody else. Okay.
So we have a question from Alessandro Roggero.
Sale, thank you for your talk. I have a question on the error extrapolation. I remember that at some point you showed, yeah. So I was wondering, here it's like, can you actually construct observables, suppose that you want to understand how the error on one observable extrapolates to 0, and you don't know that. Can you construct different observables whose errors are correlated to the one that you actually want, and then try to get the 0 error estimate on observable A, say studying the behavior of some other observable which is cheaper to compute?
Cheaper to compute, I'm not sure, in the sense that on a quantum device, computing observables is kind of challenging, because you can only compute in a single time only commuting observables, right? So the number of possible observables you have at your disposal to compute at the same time is kind of small. But in practice, in the results that I showed you here, we are effectively doing that, because we are computing observables that are similar and they match in the zero noise limit. And we essentially use the fact that they are relatively different from each other to validate results, in the sense that we have these different observables, and we are trying to do extrapolations on all of them, and we are trying to make sure that the extrapolated values of these compatible observables is the same. If it's not the same, we drop the result. Okay? And we use it essentially as a way of detecting if there was an error that our noise model is not able to capture. Okay, and that's, for instance, the reason why density of points you have in the middle here, it's much smaller than over here. That's because a lot of results in this region here got dropped because of that, because different observables that should match in the zero noise limit didn't match. Okay, and we didn't have a good explanation for it.
Thank you. That's clear.
So folks, more questions, feel free to either place them in the chat or raise your hand. There seems to be a timid audience here. So I have a question myself, and while we are waiting till the audience comes up with something. So if you think of the reducing the circuits which you're looking at, could you think of using some kind of machine learning approach to actually try to fine tune and find the most optimal kind of circuits? Have you been trying that?
I haven't tried personally. I know of groups. There is a group in Los Alamos that have been pushing that relatively heavily. So you can do very fancy things with that, in the sense that you can, one of the things you can do, you can try just to think of the limit where there is no noise, and you're just trying to minimize the number of buttons that you want to, the sequence of buttons, right? Unfortunately, solving that problem, you can prove it's an NP-hard problem, which means even a quantum computer cannot find the best way of doing it, right? But you can use a lot of heuristics to get down there, right? What the people in Los Alamos have proposed to do, and actually show it works, is you can also like perform initial measurements on your device, characterize somehow the noise in the device, and use a machine learning algorithm to find the optimal layout of gates, so that you use the best gates in the best places with knowledge about the noise in the device. Okay, so that's something very, very useful in the long run. One of the issues there is that these kind of algorithms are very data hungry. You need a lot of data, and as I showed you before here, you need to be quick in making decisions, in the sense that you cannot afford to like train your model for a week and then keep using it. You need to train it quickly, use it quickly, and check how long it's still valid, right? So you're kind of like, there is a race against the time drift, right? So in the long run, especially if you can have like hardware firmwares that have parts of these machine learning algorithms in them, so that they are helping you in real time, right? That will be very, very, very valuable, right? It's still not totally clear, like, what is like the sparsest way of representing the noise model in the circuit, so that this machine learning algorithm can do it efficiently. But there is a big possibility there for machine learning algorithms to be very impactful. Yeah.
Thanks so much. Are there any more questions from the audience here? I don't think I can see any questions in the chat or the. No, if not, we say thanks again to Alessandro here. Thanks for a great talk. And I would simply propose that we move on to the next speaker, although we are 3 minutes ahead of schedule. So the next speaker is actually Sofia Vallecorsa from CERN, and the talk is about quantum technologies for high energy physics, the CERN Quantum Technology Initiative. And that sounds very, very exciting.
Hello.
Thanks, Sofia. The word is yours.
Hi.
Go ahead.
Can you see me and hear me all right?
Yes.
Okay. Well, first of all, thanks for inviting me. This was so far a very, very interesting workshop. I hope I will not change the average here. I will share my PowerPoint, and you please. Okay. Can you see my slides all right? Great. So I will start right away. I tend to take much more time than usually allocated. So this time I cut my slides short, but I put everything in the backup. So if we end up with some spare time, I can always add, more topics to the discussion. But what I want to talk to you about is the work we started doing at CERN within the framework of the Quantum Technology Initiative, and more specifically with respect to quantum computing and quantum machine learning. So I'll try to keep short the introduction, the usual introduction about CERN, but I thought I would just keep it here in any case. We are today, our lab is today like the largest facility for fundamental research in high energy physics, but we are actually an international organization that is sitting across the Swiss-French border, close to Geneva. We are usually a very, very busy lab with a lot of scientists and associates visiting us every day. Unfortunately, this situation is currently putting all of us at home. And this is actually making it hard because CERN is currently undergoing a technical shutdown moment in which the experiment and accelerators facilities are being upgraded for the next run. And so that is actually not really the best kind of work that you can do remotely. So what are those facilities I mentioned? Well, the accelerator complex is depicted here. Our Large Hadron Collider, which is the biggest ring that you see, is a 27-kilometer ring that is close to Geneva, although mostly lying on the French territory between the Jura Lake and the Lake Geneva. It hosts 4 major experiments that are mostly targeted as multi-purpose experiments, in the sense that they are designed, in particular as far as CMS and Atlas are concerned, they are designed to do a broad range of broad spectrum of physics measurements. ALICE and LHCb tend to do more higher precision measurements on more specific topics. I would say that the general, let's say, the general feature of all of this kind of physics, of collider physics, is really the amount of data that those experiments produce, and the consequences that it has in terms of computing model and techniques for data analysis and preservation, and data preservation. So this is true today. We have more than 330 petabytes of data that are currently stored in the CERN data center. We are upgrading for the high luminosity. We are already preparing for the next high luminosity LHC run, which will increase further the resources needed to actually properly process the data that will be produced by the new experiment. So just to give you an idea, this is a projection from one of the experiments, the CMS experiments, that is comparing the computing resources in terms of CPUs that will be needed for different steps of data processing once the high luminosity run of the LHC will start. The time schedule is actually here shifted a little bit. We are late. But the message stands. current computing resources will not actually be able to give us everything we need for managing our data. Now, why am I saying this? Before going into the real topic of the talk, I also wanted to make another point. This is a slide that was presented last year at the European Particle Physics Strategy Update Symposium that happened in Granada in May 2019. It shows the typical experimental or timeline for high energy physics experiments. And what I really wanted to stress is the time it takes to move from the initial scope definition and the initial design, the initial states of experiment design to the moment in which you're actually analyzing physics. And you see that this is many, many years away. So why am I saying this? One of the first, comments that we received when we want to talk about quantum technologies for our experiment is that at least, for example, as far as quantum computing is concerned, the technology is not ready yet to be implemented and to be used efficiently in realistic use cases, at least at the scale at which those experiments run. Now, that is certainly true. However, timescales such as these ones prove that it is extremely important to come well prepared and to learn how to use such a different computing paradigm well in advance before we actually need it. What can we do concerning quantum technologies at CERN? The expertise is actually rather broad. It goes from, strictly speaking, computing applications, and you will see this is basically will be the focus of my talk. But we also have interests and initiatives and activities that started concerning quantum sensing, in particular for everything that has to do with detectors, searches for dark matter, sensitivity improvements of detectors, very low energy use cases, such as calorimeters, for example. Quantum communications is another field we are interested in. A quantum key distribution node is actually installed at CERN. We are developing a set of use cases to test not only quantum communications, but also techniques related to, for example, encryption and in general, secure data processing and analysis. And then there is everything that has to do with theory. We do rely enormously on Monte Carlo simulations and many other branches of physics and science in general. There are some problems that cannot just be solved by pure Monte Carlo techniques, or that need strong speed up as far as the real event generation stuff is concerned. And I'm thinking about everything that has to do, for example, with parton shower simulations and hadronic processes. So those are all fields that are being investigated as far as quantum is concerned. So because of this wide range of activity, a couple of months ago now, so in September, the CERN Council approved the Quantum Technology Initiative. This has primarily two main, let's say, purposes. The first is, of course, to coordinate the activities that are going on within the lab and within, more broadly speaking, within the high energy physics community. Bringing together experts from the different institutes and different labs or programs on all the major branches that I mentioned before, so sensing, computing, communication theory. At the same time, there has been a very, very large set of initiatives that have started in Europe, in CERN member states, or in other countries. And therefore, it becomes very important to also properly connect with those initiatives and integrate the overall worldwide, I would say, effort on this topic. As far as the objectives are concerned, so we are really, everything started very recently. So we are still deciding or outlining our detailed roadmap for the next few years. But we already know we have a few high-level objectives that are very clear for each one of those of the topics, of the areas I mentioned, and those are listed here. For example, as far as computing is concerned, well, the primarily objective is, of course, to understand how quantum computing techniques could be will affect high energy physics. Problem can help solving major challenges in future detectors. How much do we have to change our computing model if you want to integrate this kind of approach? Of course, all of this has to go hand in hand with a good understanding of what is the state of the art as far as software stack are concerned for simulation of quantum systems and quantum circuits, and from a point of view, from a development point of view, but also from a service point of view. So one of the ideas is to contribute to the definition of a distributed quantum computing simulation platform that our users will be able to access for their studies. In a similar way, we have defined high-level objectives for all the other areas. As far as sensing, I mentioned before, one of the major parts, or let's say most important objectives, really has to do with the low energy or high sensitivity detectors, calorimetry in particular, but also communication and theory. This is basically what I mentioned before, and I'm not going to repeat this. I would like to stress that we come into this world, into this quantum world, like a step at a time. We know we are building expertise now within the community. So a large part of the initiative is actually dedicated to knowledge sharing and training and education within the community, within our community. So let me go now to something a little bit more concrete. And I'm happy to present to you here a few of the examples that we've been working on recently in our group. As you see, most of those applications are related to different steps in the data processing chain for collider experiments, but they are actually models that solve much, I would say, more general problems. So there has been quite a few interest in quantum support vector machines. We have a few research line on this direction because those work very well as classification tools. Quantum graph neural networks have been studied for pattern recognition, and in particular, so the reconstruction of particle trajectories in our detectors. Quantum generative adversarial networks are among the most, let's say, interesting. Their classical counterpart is among the most interesting generative models that are being studied by the AI community right now, and they are interesting for us because of their applications in simulation. And so we looked into their quantum counterpart. Quantum Boltzmann machines are being studied within reinforcement learning frameworks for optimization problems. And we are also looking very, let's say, this is also one of the topics actually that I will detail a little bit more in this talk. So we are really looking into models for quantum classical data embedding. This is important at different levels. Well, it's interesting per se, but it also has a very practical, if you want, it has very practical application. Right now, most of the real life problems, or let's say real experiments problem that we try to solve, have a dimensionality that is far too large with respect to what can be solved by real quantum computers at this time. So efficient data embedding is something that could make a difference in sense of the range of application that we can actually think of implementing this way or solving this way. So as you saw, most of the applications we are studying are quantum machine learning applications. This is probably coming in some sense from, we've been developing recently a lot of new machine learning, deep learning actually, applications for our problems. So naturally, we started to investigate what happens when we are trying to take advantage of quantum effects, such as entanglement, superposition, interference, and try to use those to improve machine learning models. Now, this is, of course, not so easy to put in practice. In fact, there are a lot of questions that need to be answered. So I like very much Alessandro's talk before, because it was giving you questions all along. It was giving us questions all along the talk. So you can assume that this, basically every single slide I'm going to show you now will end up with a question, basically, because we are still really trying to understand what does it actually mean to implement machine learning algorithms in a quantum paradigm. The convergence problem in particular is a very, very important. I've added here, I'm reporting here, sorry, some, results from a paper that has been recently published by a group at the ETH in collaboration with IBM, just a few days ago, that is publishing a very interesting study about that's comparing simple implementation for classical neural networks, classical classifiers, and compare those to quantum models, and at the same time providing quantitative and practically usable figures of merit to assess performances and in some sense predict the behavior of those networks on quantum devices. Why do I say that? Because the problem of barren plateaus, and so vanishing gradients, it's a problem that is well known for classical systems, and unfortunately, it's also it happens also very often on their quantum implementations. Moreover, because it can be generated not only by the characteristics of the circuit itself, of the model, but also noise effect could actually make this situation worse. So this is a real problem. There is then, of course, as far as realistic applications are concerned, the problem of data loading. If we want to use machine learning at scale, we are usually talking about processing or inputting a large amount of data. We are not there yet, but at some point, it's an issue that will need to be understood, and that could change entirely, let's say, our whatever level of advantage we established from a theoretical point of view. And this brings me to the point of quantum advantage. Now, quantum advantage for quantum machine learning, for me, it's a very difficult, it's a difficult topic in general, but for quantum machine learning algorithms, I think it's even worse in the sense that we rarely have even established benchmarks for classical models. So this automatically gives us, puts us in a very, very difficult position. How do we define advantage in terms of quantum advantage? Do we want to look at computational advantage? Do we want to look at, samples advantage? So the idea of requiring a smaller amount of data to train our quantum models with respect to the classical one? Or are we talking about representational power? Are quantum circuit going to give us a larger, being able to learn larger parameter spaces with respect to the classical one? These are all questions that need to be answered. So variational algorithms have been mentioned already many times in this workshop. I just wanted to point out that they also make the today, like represent implementation of 99.9% of the quantum machine learning models that have been tested, and that we certainly are testing. So basically everything you'll see in this slide has been implemented in this way. They make for a very, I mean, they're very popular for a good reason. They make for very reasonable models to test on the near-term hardware. Now, the idea in this case is that they also fit very well the let's say the mindset of people that come from the deep learning world, like myself, for example. So to train this kind of model, we can use a stochastic gradient descent approach, as is done in most deep learning cases, but also gradient-free methods are being investigated to do this. For example, genetic algorithm approach. In this case, what I'm representing here, let's say, the circuit that is used to do data embedding is usually fixed. It's a fixed circuit, and the classifier, also the core of the network, is represented as a variational circuit whose parameters can be or are optimized. It is actually true that, and this I mentioned already before, there could even the step of the data embedding can be learned, in fact, and there are indications that this can actually improve very much the task of the classifiers that are run next. Besides from making it possible to, as I said before, encode larger dimensionality data into quantum circuits. Okay. What are we going to talk about? So this was my long list at the beginning. I'm going to talk to you about our work on graph neural networks and data embedding, and if I have time, I hope I do, also on quantum generative adversarial networks. If you are interested in support vector machines, I'm not talking about that because there was a very nice seminar that Professor Wu gave just a couple of days ago within the Quantep seminar series. So you have the link here. So let's start with I'm just checking time. Let's start with our charge particle trajectory reconstruction problem. Now, this is a very big issue at colliders. You see here a simulation of event in one of the experiments, one of the detectors, the Atlas detector in particular. You can imagine that this is a very, very complex problem, because each one of those colored hits here has to be associated to the right track, or flagged, classified as noise and uninteresting, and so discarded. Now, it's been quite some years that the community has started looking into a deep neural network to solve these problems, and graph neural networks have been among those that gave so far best results. The idea would be, and if you think about it, this is a rather natural idea. The idea is to represent the problem as and the detector hits as a set of connected hits in a graph, and then to classify the segments between those hits using geometric constraints. Now, this works very well. The drawback is, of course, is that if we want to go to, this is true also at the classical level, actually, this is not a problem with quantum, it's general. If you want to represent realistic events, then you end up using very, very large graphs. So I'm not discussing this problem here now, but there are solutions. Now, the GNN that has been designed and that has become our classical benchmark is built as a cascade of three networks, actually. One network that does the input encoding, and then two classifiers. One that is called the edge network and is classifying the segments that are defined among the hits, and the node network that, given 3 hits, is classifying the middle one as belonging to the segment or not. And the structure is represented here. Basically, this is the classical example, and you can see that it actually gives a very, very nice result. We have in terms of purity and efficiency. Our idea is to basically build a quantum version of each one of those classifiers and then replace them in the iterative structure. So what do we, well, yes, before describing the networks, let me just tell you a little bit more about the data. Now, data in collider experiments is not public. This has actually been a big problem in the development of most deep learning and machine learning algorithms that, as you know, require very large data and can get very good, input from a broader community usually. But it's been some years already that we've been working into making part or some of this data available. One of those examples is a dataset that has been designed for a challenge, a Kaggle challenge that happened a couple of years ago. And that represents a typical tracking problem. So we use that data set, and we applied an initial set of pre-processing at the classical level with the sole purpose, with the simple purpose of reducing the data dimensionality in general, and of cleaning up, the most, let's say, difficult tracks, those that, for example, have a very large curvature or very low energy. And so for the input to the quantum circuits become what you see down here. For the edge network, the input to the network is basically the 3D coordinates of the 2 nodes of a segment, and the network outputs a probability that the segment belongs to a trajectory. And for the node network, we input a triplet. So the coordinates of 3 points, and the output is the probability that the target node is actually good. So what are the architectures we use? We use hierarchical quantum classifiers, and in particular, 3 tensor networks at 3 tensor networks. Now, the idea is that they are simple to implement. You can see an example of a 3 tensor network here, where you have your alternate layers of rotations and entanglement gates. They have also been proved that it has also been proved that they are rather robust against noise. Although all the simulation that we've done so far for our tests do not include noise. So this is some results that I'm quoting here that shows this was a test that was run on the IRIS dataset, which is just a dataset with images of flowers that are being classified. And you can see that the classification accuracy stays very stable, even when the noise is increasing. Although the error bars here on the accuracy, the result, the measurement, the uncertainty on the measurement becomes worse. This is the architecture of our network. Well, the idea, you can recognize here the iterative structure. Have our nodes information that is initially goes through some input layer. This is purely classical, a multi-layer perceptron that is building the input features for the quantum network. The second input is what we call the graph connectivity matrix. This is just basically giving us some initial information about what building segments out of nodes, out of hits doublets, basically. And each one of those hybrid networks is represented here. So we have the input circuit that is built as a set of rotational gates, Y rotations, and then we have the parameterized quantum circuit that is represented as a TTN here. So I show you here results. The baseline, our first test is implemented using the TTN as a comparison. This was also compared against two other tensor network. So a merograph, which introduces a little more entanglement in the topology of the graph, and it's supposedly it's capable of taking into account longer range interactions, although the effect here is very small with respect to the TTN, but it could be because of the structure of the neural network. We are actually trying to optimize the particle trajectory a little segment at a time. So long range interactions might probably not be so interesting, might have such a big effect. The MPS, the magic product states architecture has also been tested recently. You can see that this is a very recent test. We don't really get as well such a good performance, neither in terms of loss or in accuracy in the area under ROC curve. As a comparison to classical networks, well, you can see a comparison here. So the blue curves represent the original classical implementation with different depth layers. So with just a single node edge iteration and 5 and 10. Well, the accuracy is actually the difference in accuracy is not so big. As you can see, they all cluster here around 80%, which is very good. When you start to increase the performance of the depth of the classical model, you can see that this is actually moving higher, but not so far away. It moves up to 84% while using a much larger number of parameters, which is the x-axis here. I think I still have some time, right? I wanted to quickly touch on the embedding part. Now, as far as the classical approach is concerned, we realized that we could actually make a much better, obtain much better performances by trying to use a better representation of our input data. Now, this is you see how it happens, how it works classically here. This is the status of the representation in the XY plane of our detector hits here. Now, if we use a multi-layer perceptron that is trained to optimize the separation between hits that belong to the same trajectory with respect to some seed or that don't do that, and you can do this by using an inch loss, then you can obtain this kind of representation where you can easily let's say, select the events that cluster closer to the seed. And then if you do that, then you can see that transforming back in the original plane is actually giving you very, very nice results. So what we've decided to do was to try and understand if we can turn this into a hybrid quantum classical embedding and improve also the performances of our circuit. Now, this is some work that a student has been doing through the summer with us, so it's a very recent work, and it's still preliminary, but we already find some interesting behavior that I'm just briefly going to show to you. So I mentioned the standard classical embedding is using multi-layer perceptron with 10 hidden nodes, each one of them as 10 hidden layers, each one of them has 512 nodes. We match this to a quantum circuit, and then we read out the quantum circuit output, and we just use an additional layer just to rescale to whatever is the needed dimensionality. Now, what kind of tests do we do? So machine learning, the MLP output is encoded as a set using as before, as I mentioned for the GNN, a set of Y rotation gates, and then we test different kind of architectures for our variational. Sorry, this is not a variational approach. We also tested the variational approach, but I'm not going to talk about that now. So we chose our a few different topologies for our circuits. Those were actually studied in the reference that is mentioned here. This is work from the University of Waterloo, which made some interesting proposals for measuring performance of quantum circuit for characterizing performance of quantum circuits in terms of expressibility and entangling capability. And so you can see the definitions here. Well, I also have them in the back slides if you want. But the idea is that when you're measuring entanglement, what you want to see is higher features here, and expressibility gives you a measurement of how much of the Hilbert space your circuit is capable of covering, and is measured as a Kullback-Leibler divergence, and therefore the lower number you see here, the better result. So you can see that we chose different topologies for our circuits where the entangled is done in different ways, and with different number of parameters. This is reflected also here. Unfortunately, this also means that we have very different training times. Now, here are the results. The table is the same you saw before. I just put it here for convenience. Now you see that we have trained our hybrid network, our hybrid embedding network for a very short time, actually. This is because of computing resources limitations, but we managed to observe some differences. Now, the error bars you see that are associated to the validation loss are due to the statistical uncertainties on those losses and the instability of the training. Now you see clearly that some circuits, for example, the circuit number 5 exhibits larger uncertainties and larger instability in training. In fact, we even hit barren plateaus a few times. Circuit 14 and 7 are the ones that seem to converge faster. But again, those results are preliminary because the situation might change when we actually train over a large number of nodes, of epochs. We've also tried to see if we could improve results a little bit by increasing the number of iterations, or the number of times we repeat those basic circuits in the hybrid architecture. This you see plots for the circuit 14, which is the one that used to give us the best performance, and you can see that actually I don't know if you read the scales, but if you go from here from a single iteration up to 5, we are actually improving the entanglement quite a lot. But eventually the curve flattens out, and the same for the expressibility. Moving on from 1 to 5, we actually see that we don't gain that much when we move from beyond 2-3 iterations, although this is a log scale. We also tried increasing the number of qubits. Our initial test uses 4 qubits. We try to go to 8. This means that basically the classical MLP is outputting 8 features, or 4 or 8 features. Basically, we didn't really see, I think within error bars, the two curves are very, very close to each other. So, for now, our statement is that we don't really see a big improvement in changing the number of qubits. Now, I think I'm running out of time. So
if
should probably close here, right?
Yeah, if you could wrap up, because then we have some time for some questions.
Yeah. So let me go to, I will skip the part on generative models. And sorry. And I will just conclude. So we have established at CERN a quantum technology initiative that it's aimed really at assessing the potential of quantum computing for our community within the timescale of the high luminosity LHC and further experiments, so and beyond. A large part of this is really related to try and build expertise and skills within our community and understand what are the challenges that are related to actually integrating quantum computing in our computing, our approach to computing. As CERN Open Lab, we've also started investigating a few opportunities of introducing quantum computing in particular our machine learning applications. The idea is that most of this work is done not only within CERN, but also in collaboration with different actors in other institutes and in the industry. And I would really like to stress the importance of collaboration with industry at this time, because they are really at the it's important from a point of view of hardware development and at the same time of optimization of algorithms and software. So it's really important at many levels. And as far as more precisely our studies on quantum machine learning are concerned, the idea is try and understand if we can spot hints of quantum advantage, but more than that, really understanding what does it mean to actually train a machine learning model on a quantum computer, and that's all. Thank you.
Thanks so much for a very inspiring talk, Sofia. So we already have some questions in the chat by Andrea Delgado. Can you read them, or you want me to read them? There's several questions here, actually. Yeah.
The point. Let me see, because I have minimized.
Yeah. So there's one, can you elaborate on what a distributed QC simulation platform is? Would this be a general purpose tool like root for analysis or ML specific?
Oh, okay. Now I'm reading it, yes.
Yeah, okay.
So, well, it's both, in the sense that what we would like to achieve is building up a collaboration with different institutes. We would like to achieve something that's similar to WLCG today. So the LHC computing grid has been this distributed computing system that has allowed the community to process most of its data. Now, if we could come up with a network of centers in which we could distribute our quantum computing simulation, then we can give access to enough resources to do large-scale tests to the community. Basically, most of the examples that you saw that we studied were actually limited in terms of dimensions because of classical computing resources to run the simulators. So we need HPC centers basically if we want to go beyond a few tens of qubits today. So this is something that if we want to at some point solve a realistic problem, we need to assess.
So the rest of the people here.
Thank you.
Yeah. Come. So do we have,
Sure.
More questions, please? We still have time for some more rounds of questions here. So while people are punching in their questions, I have one. So I got intrigued by the quantum support vector machines. Is that an implementation of the standard convex optimization problem on a quantum computer? Is that what they were thinking of? You had a slide there on quantum support vector machines, right?
Yes, in fact, I have. Can you see my slides again? Yes.
Yeah.
So I had it in the backup slide. So what we are trying to solve with that, maybe I should have gone. Okay, I'm there now. What we are trying to solve is a classification problem. So this is applied to a signal to noise kind of classification for a specific use case, physics use case. So we are building. This is built again as a variational circuit, and it is using as input a set of let's say, high-level features. So already physics variables that are the output of actually a very large preprocessing, and that then just optimizes mean, what's it called? An MSE kind of error.
Mm-hmm.
So just a mean absolute error, kind of loss. Now, this is, so it's a very, very, very standard kind of circuit. The results that I have are not the latest. So those are actually from some months ago, and they were run on the IBM hardware. You can see, well, you can see two things. I mentioned before here the fact that we need to run the support vector machine on a limited set of features. So there is here a comparison to the effect of limiting the number of input features to the final accuracy. And actually you see that this is not a problem for the quantum implementation. And here you see also a ROC curve. So the accuracy and error and background rejection on for the quantum SVM is represented by the red curve here, and it's compared to classical implementations that are here. So you can see that it's pretty much consistent. You see this also with the table that summarizes the whole area on the curve. So this is the SVM. This is actually one of the SVM implementation. The latest results are presented in the seminar I mentioned, the professor who gave yesterday, 2 days ago. They have updated these results and included measurements on Amazon Bracket actually, and on Google hardware. So this is it's a very interesting.
So the results which you show here for the quantum support vector machine, that's a simulation which has been done on an actual quantum computer, right? It's not a.
So the green, sorry, the red line is actually it's a simulated circuit.
Okay.
The yellow line is the output of the real result obtained on the real hardware. And this is a 20 qubit IBM machine. The code name is here. Well, the result has improved today in the sense that if you look at this plot, you could see that there was still some discrepancy between the result that was obtained on the hardware and the simulation here. So there was some mismatch in the noise simulation, I believe. This is no longer the case with the updated result.
It was very interesting. Thanks. I think we are running a little bit. Yeah, we're actually on schedule now. If we have to stop here now, so we should say thanks to Sophia again for a very, very interesting talk. And
thank you.
The last speaker today is David Dean, and David, we should actually, as participants here, congratulate David with having become the director for the new Quantum Computing Center at Oak Ridge National Lab, which is a big enterprise supported by the DOE. And having known you for many, many years, I have to say I'm very proud of what you have achieved and what you have achieved together with your colleagues. David, please go ahead.
Thank you, Morten. So I'm going to turn on my, everybody can hear me, right?
Yeah.
So there's a problem over on Teams a few minutes ago. So it's really a pleasure to be here. Yeah, so the Quantum Science Center, you see the sort of the artwork we pulled together to talk about quantum science. It's really my head blowing up, what you see on the screen. It's very difficult to know that any jokes actually make sense on the web, but I thought I'd tell that one anyway. I'm not going to show slides, but I am going to kind of walk through a few points about quantum computing mainly, and where we are and maybe being unable to really attend a lot of the sessions, except a few of them. That was a great previous talk, and I was able to attend a good number of the talks yesterday. I just wanted to give a few points and go from there. So as many of you know, I mean, we're building on the shoulders of great scientists who've really plowed the field and tried to give us a hint of where we're headed in quantum computing, starting with Feynman, but you can think of Dave Wineland, you can think of Peter Shor, just a whole bunch of types. John Martinez over at, well, UCSB now, David Deutsch, John Preskill, tremendous people who have worked on quantum computing, either theoretically or worked on the ideas of quantum computing or the hardware, trying to understand how to trap ions, for example, or how to make superconducting wires. These people have really done tremendous things for us. So we really kind of stand on those shoulders of those men, as Newton would have said, those people. And in the next 15 years, 10 years, we're going to make plenty of errors as we move forward. And I think it's important to realize some R&D is just going to fail. It's just going to fail outright. We're not going to have the error noise under control enough. And so, you know, things will happen and we won't have the right results out of our computers. But at some point, some R&D will succeed amazingly. And we already have seen a lot of that, a lot of indications of R&D, both in the algorithm space and also in the hardware space, really starting to take off. So there's a lot of promise. There's a lot of activity that could really develop into things where you could solve BPQ problems on the computers. That'll be an important day when that happens. We will need ways to build collaborations during the time, particularly over the next year. I was just on a phone call with our students and postdocs of the Quantum Science Center. There are about, right now, today, there are about 20 of them. And we think we'll grow that number up to about 40 over the course of the next year. And one of the students said, well, you know, it's all great to be online, but I really miss the activity of drinking beer with my colleagues. Okay, point well taken. You know, we don't have the ability to actually meet at Trento. We don't have the ability to actually meet in person. And I think from my own personal experience, that's just a missing element. So building collaborations over the next year or so is needed and will be a challenge for all of us as we move forward. I think a fourth point, there are three types of problems in quantum computing. There are probably more, but these are three that I could think about. You know, finding algorithms that work. The ideas are there, but the algorithms, how do they work? What are the limitations? If you're mapping a particular system, particular quantum system onto a quantum computer, how strong can the interactions be before you don't have a breakdown? What are the breakdown in the computation? What are the limits of the computation that we can do? There are other types of problems. Finding the problem set that answers a burning question in the physics that we're doing. You know, we start with helium or hydrogen or deuteron nucleus, and we build up to heliums. Can we go further so that we're in areas where we're actually doing something that's relevant for nuclear physics that hasn't been done before? Similar question could be asked in QCD space. I think there are sets of problems out there where, you know, time dependence might be important, fusion problems, fission problems. But getting there from here is going to be one of the major driving issues within the research set. And then maybe a third area understanding which problems don't really need quantum computing. You know, you don't have to use a quantum computer if you have some of the world's fastest computers flying around it in Germany or Italy or the United States or Japan. And so what is the class of problems that where the promise of quantum computing really actually meets the physics that we're trying to get out? Those are three types of problems in QC: what not to do, what to do, and how to do it well. I think that would be another way to say it. The field is exciting. I think you can hear that from the various talks and speakers. Also, the machine learning field is extremely exciting these days as well. And back in the 80s and 90s, when you could make little simple neural network algorithms and make them work to identify letters or something, I'm sure that a number of us played around with those algorithms. But today you can really make your learning algorithms do things for you, like characterize the detectors and stuff like that, in a fascinating and interesting way. And because of the excitement of the fields, both quantum computing and machine learning, there's a lot of young people in the fields. So that gives us a responsibility, those of us who are a little bit more senior now, to guide those guys, our students and postdocs, in a good way, to give them problems that will help them to flourish. I think that's really one of the big excitements in the area. Another one is the variety of ideas that you see out there. This week we had a meeting of the 5 center directors of the Quantum Information Science Research Centers. These are the DOE, Department of Energy centers in the United States that have just been stood up. We're all only 40 days old, actually. And within those centers, you see a number of different ideas that will be pursued. That variety of ideas, variety of platforms on which to work really makes this an exciting time. And I believe that's why you see a lot of youth involved, a lot of early career folks involved in the science. And then there's just the interdisciplinary nature of the science. Quantum computing really requires one to understand how to build an algorithm. This is sort of like the days of machine languages, you know, puts and gets and pops and all that kind of stuff. And so you have to figure out how to make an algorithm that will work on a quantum computer. You have to, which is one aspect. You have to know algorithms, which is another aspect. It's more like applied math efforts. You have to know some physics. That's another aspect. And if you're dealing with the actual implementation of devices, you have to know some engineering. And so across the board, I think in the various activities that are going on in quantum computing, you see a lot of interdisciplinary nature. And machine learning has that same kind of feel. I was at a conference last year in Washington with about 200 people that were writing a document for DOE on machine learning and how it could impact the various scientific activities. And you saw a whole lot of people there who were applied mathematicians trying to understand what the physicists needed. So I think that's also an area where there's this great interdisciplinary aspect. And then, of course, there's a lot of funding coming into the area right now. In quantum computing, you know, $625 million from the government, just in the announcement of these centers. Lots of research opportunities in the base programs within the Department of Energy at the National Science Foundation. Speaking more of the US, where I'm more familiar, but I also know that there's a lot of funding coming in Europe and in England and in various parts of Japan and China. And all of those funding efforts mean that there are lots of opportunities to do some original and interesting research in the area. There's also a lot of venture capital out there. As a National Lab employee, I don't go after venture capital, but a lot of people do. And it's also an interesting time in respect. So generally speaking, because of the promise of quantum to be able to do problems that you can't really do in other ways, because of the promise of machine learning to help us understand complex data sets in ways that we really can't do right now. Both of those really have this aspect of great promise. In quantum computing, there are two major roadblocks that I see, maybe three. One of them is just robustness or the resilience of the quantum computers. How long do states live? For example, the atom in an atom trap can sit there for a long, long time, but it takes a long, long time to compute something in the atom trap too, in the ion trap. The superconductors live a short time, but they run fast. So there's this balance that one needs to be able to understand how to compute things in a manner that you can compute before the time runs out, where the quantum system basically diffuses. You don't have the ability to calculate. So T1 and T2 errors and T2 star errors have to be controlled. And I think those are big technical challenges that have to be overcome. And then the scale up to larger problems. This is, right now I would say we're in the era of toy problems where we kind of know the solutions. Either we kind of know or we absolutely know the solutions. And that doesn't mean that the computer can actually tell you something, quantum computer, or give you insight into physics that you don't already know. And so we have to really scale quantum computing up into the ability to learn new things. Now, if you think back in what was happening in HPC 20 years ago, 30 years ago, you had kind of a similar feel. You kind of knew some of the problem sets you could work on. You could work on simple problems with the computers of that day, of that time, 30 years ago. And they were still useful for solving problems. But if you look back, the problems that they were solving were kind of the toy problems of today. And so the evolution of HPC in algorithm space and in hardware space, kind of coupled together, really brings us to today's forefront HPC systems, which are solving problems that just can't be tackled in any real way. And so I think the same kind of evolution is going to happen in quantum computing, where you're tackling today really kind of toy problems where you kind of know the answer. But in just a few years, you're going to tackle problems where you don't necessarily know the answer. And that will be an interesting and fascinating transition as we move through. What can we learn from previous experiences? Well, quantum Monte Carlo is something I worked on in the 90s. And I think what we learned there is that the sign problem just kills you. And we kind of knew that, but we thought we could overcome it in certain tricks in certain ways. But at the end of the day, it just didn't really pan out to be a panacea. It was good for certain things, good for thermal properties. This is in nuclear physics. Quantum Monte Carlo is shell model Monte Carlo or auxiliary field Monte Carlo. But you couldn't really do things with it where the experiments were going at the time. So there were limitations. You think about coupled cluster theory more broadly now. In the 1950s, Fritz Koester kind of wrote down the equation, wrote down the ansatz for coupled cluster theory. In the 1960s and 70s, people really worked hard on making problem sets that could work in nuclear physics with coupled cluster theory. But they were trying to overcome an interaction which had a singularity, basically a large, heavy repulsion. And so the theory kind of broke down. They made progress, but it was limited. Whereas people in chemistry were coming up with all kinds of interesting algorithms and ways to do coupled cluster theory in a better manner. And it wasn't until around 2000 that we picked it up again in nuclear physics and ran with it. and started to try to understand how it could attack real problems that were interesting to the field at the time. And if you look at quantum computing, it's gone through a similar type of evolution. You know, in the 80s, the theory was the idea was there in Feynman and Benioff and other papers. Other people were expressing it. It was developed for 10 years as a theory, as a theoretical onslaughts. And in the 90s, certain experiments started underway. I would say that you know, the late 90s, there was a kind of a death, not a full death, but kind of a reflective moment where people said, well, I'm not so sure this could work. And then as technology improved in the early 2000s to mid 2000s, and you started to see components of quantum computers, the atom traps or superconductors, start to really ramp up. Then you began to see the field explode. So I think this is where we are today. We're in an explosive environment of new ideas and new things, new challenges within this, and let's see what happens. You know, I think over the next 10 years, maybe we'll find out what lives and what doesn't live. I think I'll just kind of conclude by saying, you know, in the next 10 years, I think someone is going to demonstrate a fault-tolerant approach, even in the NISC computers. Somebody, there'll be enough qubits to try to do simple error correction, and if there is, there will be a further explosion of ideas at that point in what can be done and what can't be done. Somewhere in the next decade, you know, people are going to approach the Hubbard model and look at the phase transitions within that model on a quantum computer. QCD at finite baryon density is a major challenge. Maybe quantum computing can work there. And then in nuclear physics, maybe fission, although that's a little bit large in terms of nuclei. Maybe nuclear fusion activities, such as I think Guadaloni is trying to do, can be looked at and more precisely understood. Various time-dependent evolution ideas should be available through quantum computing. So just to conclude, I think we're in the middle of the beginning of the quantum computing era. I think it's a long era. It's gonna, you know, starts in the 80s, really explodes today. I think we have 10 to 20 years of incredible research to make this really valuable to the full community. Really to tackle the evolution of high performance computing and how the quantum computing can accelerate high performance. That'll be a fascinating and obviously interesting research and discussion as that happens. And we're right in the middle of it. And the people on the phone are people who are thinking about these problems and really working on them across Europe, across the United States, and in Japan and in Asia. And it's an exciting time. And so I'm just looking forward to doing my little part to help this field along and to work with others, work with you all to make this field a successful endeavor. So I will stop there, and I hope that this has been a great workshop. It was fun to organize. I really regret not being able to attend a lot of it, but I am excited for the field and excited for you all. Let's see what happens.
Thanks so much, David. Thanks for all your thoughts and words. So the kind of idea we had as organizers was that David could give us some inspiration, and perhaps we could open up for discussions. I mean, if people have inputs, ideas, thoughts they would like to share with the rest of the people here, feel free, again, unmute yourself, raise your hand, or write your comments in the chat. But we have a pretty silent audience today, right? So Any comments? Yeah. Here we have Thomas.
I have a question, David. Nice overview. I wonder, so from the 5 centers, at least in the US, what is the expectation also for regarding having a quantum computer that can solve problems we cannot solve classically in 5 or maybe in 10 years? What are the odds there? What is the sentiment of the people who are driving this?
It's a great question. I think the you know, in each of the centers, it's a little bit different activity, of course. The QSC is really focused on topological, working on topological materials to make qubits that are robust against error. The 3 of the centers are focused on superconducting. The one at Brookhaven, superconducting with IBM. The one at Fermilab, superconducting in cavities with Rigetti. And the one at Chicago, not really superconducting, but more communication between qubits. And then Irfan Siddiqui at Berkeley is looking at fault-tolerant algorithms and how to build them and how to match your algorithm toward your computer, so to speak. Kind of giving I would say, a LinPack or a QLinPack for the algorithm space. I think each of the center directors feels like this is more a long-term issue than a short-term. It won't happen today. It won't happen tomorrow. But you can feel how IBM, for example, is moving. They will move into over 1,000 qubits by 2023, and if they can figure out how to push that noise level down, if they can figure out how to control the noise level, I think you might see actually some interesting algorithm building going on there that could be useful to solving problems that are in the sciences. And so, you know, that's the goal. I think it's still 5 to 10 years out.
I think there's an interesting comment from Zora here in the chat. Can you read it?
Yep, I see that. I know, I see that. It is exciting. I think Chris has.
Hi, David.
Hey, Zora. I think Chris has, you know, and actually just generally, when you're trying to do quantum simulation, rather than doing full gate sets and all that stuff, you can actually get some stuff out. And there's no doubt. You can look at phase transitions, for example, in various types of material settings. And both Chris and also Mikhail, lost his name, but the Harvard guy. Misha Lukin, both those guys are really pushing the boundaries there and doing great stuff. So I don't disagree with you that you can definitely do some stuff on this hardware. I think full gate set type stuff is a little bit more tricky. Yep.
I agree, yes.
So we have a question from Sofia Vallecorsa here. Sophia, go ahead.
Yes, it's a question and comment. Sorry, I show myself otherwise. So I was just thinking if you have, if you could comment on any, you know, even long-term strategy to actually make hardware resources available to the communities, you know, because right now the way we access in most cases quantum hardware is through direct either collaboration with the companies or through cloud providers, for example. Is there any plan to, you know, change this or integrate this in any way in the computing infrastructure?
Yes. So I'll answer for Oak Ridge National Lab here. Okay. So what we've done is we've instituted a user group, user yeah, user group at the OLCF. The OLCF is our leadership class computing facility at Oak Ridge. And within that, there is actually a quantum part of that where we are providing access to cloud computing, the various, cloud computers, IBM, whatever, Getty, Cold Quanta, whatever. And we're doing that through proposals. So this is a formal DOE proposal-driven process through the user facility where proposals come in, you vet them, and then time is awarded just like you would on a conventional HPC. Time is awarded based on what proposals can get through. And so I think that's kind of a longer term goal of the laboratory and also of DOE to set up this kind of mechanism so that it's not company, experimentalist or person researcher company relationship. It's more researcher through a national user facility. So that's what we're up to in the United States.
Yeah. I think it's very good. This is something we should aim at also here. I mean, definitely.
It's a good idea. Yeah.
Thanks.
Well, folks, more questions, comments to David? Or if you want to share some thoughts about the future, feel free to do so. I see we're getting close to the hour as well. Let's wait a little bit and see if somebody else wants to share some thoughts here. So David, if you look at some of the candidates which you're thinking of at Oak Ridge for topological quantum computers, what kind of technological problems would you have to face in the near future?
So there are a couple. So I think the just to give a brief insight to what these things are, you get the topology by going to 2D. So the material goes to 2 dimensions. You can think of the fractional quantum Hall effect as an instantiation of this. So you're dealing not with you're dealing with fractionalized statistics, so that anyons come into play. And in a 2D material, the anyons are really combinations of electrons and holes, or electrons and electrons. And so that's the first point. So you have this many body problem with quasi-particles that are running around in 2 dimensions. And then you have to figure out how to get those quasi-particles to basically revolve around each other. So if you see my fingers, they have to go in 2 dimensions somehow around each other. And if they do it in such a way that, in our conventional way of thinking, you take 2 particles and you interchange them, they're fermions, it's a -1 in the wave function, right? It's basically what it is. If you do these anyons, it might be -2/3 in the wave functions. The other thing you have is abelian versus non-abelian rotation. So in abelian rotation, you do the rotation around, let's see, I can't really do that here. You do the rotation around 1 and you, or around twice, and you pick up the same wave function as you had before. In non-abelian, you do that rotation around and you pick up something different. And so that non-abelian aspect is what you need in order to make gates in this stuff. So the QSC is really focused on 1, the anyons, how to make them, this experimentally, and 2, how to get them to braid, how to get them to interact. That's where actually in 5 years we think we can get. In terms of experiments today, anyons doing abelian braiding have been demonstrated just recently this year by a group led by Mike Manfra, who is part of Station Q at Microsoft. It's the non-abelian part that's going to be the challenge. And so, that's a long-winded answer.
But if you look at I mean, would there still be space for, let's say, a quantum engineering with a standard many-body method, just to see how the system develops? And because that's what we've seen when we've been running time-dependent couple cluster theory for quantum dot systems, that you can really do some quantum engineering and help the experimentalists in setting up the optimal gates for doing specific.
Exactly.
Yeah.
I think that's what's needed.
Yeah.
I think forcing yourself to go from SU3 to SU2, first step, and then thinking about what an anion really means, second step. Writing down some equations, trying to solve them within that problem, and then understanding, how you actually see an anion in a material. This is hard work. This is from an experimental point of view, this is a tough job. And papers are out there that say yes, we can see them, and other papers are out there that say no, you didn't see them. So I think that's where the rubber meets the road, and as a theorist, that's where a lot of insight needs to be driven, and that's how we can help. Yeah.
By the way, I see we've gone beyond the hour. So, are there any more questions to David? I don't want to monopolize the debate here. I'm asking more and more questions. Because if not, because if not, on behalf of the organizers, we would like to thank everybody for making this a truly enjoyable workshop. Thanks to everybody. And thanks to David, thanks to Sophia, and thanks to Alessandro today for excellent talks.